सही है. अच्छा, what I intend to do, we missed few classes, though we tried to just play the old videos, and somebody also took a lecture, but I am planning a 3-hour class on Friday, okay, from 6 to 9, and we'll try to cover whatever I could cover in 6 hours in those 3 hours. If not, then we'll spend more time, but this is what I plan to do. And so I'll continue doing what I was doing, and basically we covered discrete time Fourier transform, and we were about to start Z transform. So we'll start from here, assuming that just continuing from where we left, and this is where we left. We said transform which translates a signal from time domain to frequency domain. And another way of conceiving the idea is that this is a transform which tells you about all the complex exponentials which are there in a signal. Okay, that's another easy interpretation, because you need a good interpretation. And interpretation is, it tells you that what all complex exponentials are there in the signal. For example, in cosine of omega naught n, I know there are two complex exponentials. One is an exponential of j omega naught n plus exponential of minus j omega naught n divided by 2. So at these locations I'll get two impulses. So this tells me that there are two complex exponentials at omega naught minus. So one frequency, but because the transform, the discrete time Fourier transform, is about the exponentials, that's why in a cosine you see two of these. Okay, one on the right hand side, the other one on the left hand side. So if you find two more here, what does it signify? There is another cosine in the signal. If you find, let's say, another one here, what does it mean? It means there is three sinusoids in the signal. But if you find something like this, it means there are many. Every perceivable frequency from this to this. So all these cosines are constituting the signal. So it's one way of, because that will help you to understand. And now remember that a linear and time invariant system can vary the magnitude and phase of these complex exponentials. Okay, so basically, so you have all these exponentials, and then you have a way to eliminate them, to amplify them, to move them left or right, and that is what a system does to complex exponentials. This is where we left. So this is a mathematical transformation, and there are several mathematical transformations which exist, and people use them for one reason or the other. A good reason to use a discrete time Fourier transform is to find out the frequency contents in a signal, the exponentials. Okay, then there may be any other transformation which will tell you something other than this. Another look at the transformation also tells you that once you compute this, it basically tells you that, okay, these are exponential with this magnitude, exponential with this magnitude. This is also important, that a signal consists of exponentials, and their relative magnitude will tell you their relative contribution in the signal. Sometimes you don't want to see the exponential. You say, perhaps I know this signal consists of not exponential, for example, because I have done it. Let's say I am constructing a signal which consists of several functions, maybe tangents, and I say, okay, I think I can break the signal down into so many tangents. Right? Or this signal consists, for example, a vector. We know a vector consists of I and j if it is a two-dimensional vector. So every vector can be perceived in terms of I and j. Knowing I and j, you know where the point is. In three-dimensional space, every point in a three-dimensional space consists of what? I, j and k. Okay, so these are the basic components, and you have a way to divide a point in space. You know, a point in space is basically 3 vectors. Similarly, a signal, once we talk about a signal, say, I think this signal consists of so many of these functions. Putting together will make that function. And this is a very interesting interpretation which is used a lot. And we'll keep seeing this in transformations. Then there is another transformation which does not really give you, which does not give you the frequency contents, which tells you something else about the signal or a system. That is called Z transform, and I have already studied this. So Z transform is another transform, and the reason for creating another or using another transform is that if this Fourier transform we know is only valid if xn summation is absolutely summable, so it is less than infinity. Okay, if it is not, then you cannot use discrete time Fourier. You cannot compute discrete time Fourier transform in closed form as a closed form expression. So and people have tried another transform by introducing another factor in the signal which can bring the absolute summation, which brings the absolute summation to some finite number. Because mostly we will only be dealing, for finite signals you don't care, because finite signals are always absolutely summable. Our only worries are about the infinite signal, and in infinite signals you will deal with nothing but exponentials, right? So in infinite signals you only deal with exponential in signal processing. So deal with exponential, you say, okay, this is an exponential a n u of n, I need to deal with this. Okay, this a will decide whether this is absolutely summable or not. We know that its magnitude, absolute magnitude is less than 1, then it is absolutely summable. If not, it is not absolutely summable. So I can put another factor which can always make the thing in the bracket less than 1. If a is greater than 1, I make r even greater than a. Okay, something divided by something which is greater than that will always result into something which is less than 1, will make it converge. Okay, I'll still take the Fourier transform, but I introduce this factor r. To make sure that I can take the transform. Okay, and so in Z transform our entire interest is in finding the values of r. The values of r, there will be a range of values of r which can make this expression converge. So that is our interest in Z transform. So our interest in Z transform is not in actually computing Z transform, actually plotting Z transform. No, our interest in Z transform is finding that r, and I'll tell you why, because it is where it is used. Because we just don't compute transform for the sake of computing transform. Transform gives us a lot of information which is otherwise not available. Right? So r is an interesting factor, and the value of r will help us to decide about the characteristic of the system. So r, I'm saying you introduce this r into the exponential and then find out the values of r, the range of values of r, which will make this whole thing in the bracket less than 1. For example, if this is the sequence 2.3 raised to the power n u of n, I know this will not converge. This is a diverging sequence. And now if I say, okay, don't worry about it, let me put this r here. Now, is there a range of values of r for which this will converge? And answer is yes. What are those values? You say r should be greater than 2.3. So you say r is greater than 2.3, this will converge. Now you can take the Fourier transform of 2.3 over r raised to the power n, and specifying that r is there and r must be greater than 2.3. Okay, and because r here is a radius, a value which is greater than 3, you make a circle. You say r is 2.3 and this is what it is. Okay, and you shaded, you say this transform, the Fourier transform, is only possible if you introduce an r which is greater than 2.3. What happens if r is equal to 1? Not in this case, otherwise. If r is equal to 1 means what? It is the same sequence. It is the same sequence means it is the same Fourier transform. The same Fourier transform means that Fourier transform exists when a sequence is absolutely summable, or if it is a system, it exists only for stable system. We said the Fourier transform only exists for stable system. Why? Because we know that the check for stability is if a system impulse response is n. This is the check for stability, that h of n absolute value must be less than infinity. It means that if this r, if 1 is this is unit circle, if you can find the Fourier transform, it means system is stable. If you can find Fourier transform, because the Fourier transform only exists for stable system, okay, or Fourier transform means r is equal to 1. If this r is equal to 1 can make this sequence converge, then it is a stable system, okay. R is equal to 1, if r is equal to 1 is obeys this. In this case it does not, because r is greater than 2.3. I know this sequence is not stable. Now a question comes in our mind that what is the point? By looking at this I can know whether it converges or diverges, right? What is the point in just going through this entire exercise of saying something will converge or diverge? Once by just looking at the sequence I can say it converges or diverges. You can say by if there is only one exponential. Okay, you can say if the system is written in this form, but usually system is written in a difference equation form. In a difference equation you don't know the exponentials in there, okay. So the Z transform is a transform which is used not to check the frequency contents but to check the stability of a system. Z transform is used to check whether a system is stable or not, okay. It's a very good transform, but it is, and to check the stability all you need to know is R. So I'm not interested in the Z transform and how it shapes, and I'm only interested in knowing that what values of R will make the exponentials converge. Is that value of R contains the unit circle or not? If not, it is not stable. If it contains, it is stable. I'll give you another example. जी. But if the reason is you have to compute Fourier transform. ठीक है? I don't want to compute Fourier transform. I just looking at it I want to say whether the system is stable or not. So you have to put it in an equation. You need to run an algorithm and then you find out, oh, this is not giving me any value. ठीक है? I don't want to do any computation. I design a system and then I want to say whether it is stable or not. It is easier if you are designing it offline. But remember, in this the second part of the course we will be designing on the fly. You say you design for few milliseconds, system is this, now system is this, now system is this, and there you need to make sure whatever you design is stable, and that is dynamically, especially in equalization problem, all the time you are designing system on the fly, and you have to check whatever you have designed whether it is stable or not. Z transform is used to check the stability of a system, okay? And you don't compute Z transform, means that you don't need to, as you compute Fourier transform, you plot it, you see the frequency contents, you don't do that, because Z transform is also Fourier transform for R is equal to 1, okay? So coming back, if I say that okay, this A is 0.9 and this is R, so what values of R will make the system converge? R greater than 0.9 will make it converge. This is stable because it is 0.9 is here and we say it is stable because now the blue circle is inside the region of convergence. Okay. So this is the motivation of computing Z transform. The motivation is to comment on the stability of a system, and our interest is not in finite impulse response system, our interest is in infinite impulse response system, because their stability is a question. So you don't compute Z transform for finite system.
Transform का मकसद ये है कि stability को चेक
जी जी
सिंपल चेक हमारे पास मौजूद है h of n
his question is that we have a simple check h of n, and I'm saying once you check, let me put a difference equation. Y of n is equal to 0.85 y of n minus 1 plus 0.6 y of n minus 2 plus 0.7 y of n minus 3 plus x of n. Okay, the question is, once you know h, you don't know h of n, you know the difference equation. Okay? Looking at the difference equation, I really cannot comment. So I have written it myself, I cannot comment whether this is stable or not. I have no way of looking at it and saying the difference equation represents a stable system or not. Don't be misled by these 0.7. These are not exponentials. We'll find out once we go through the Z transform. These are not exponential. These are just coefficients of the equation. This may or may not be a stable system. And my take on Z transform is that I want to comment on this, whether it is stable or not, without computing the impulse response. One way is that I go through, compute the h of n, and then check all the exponentials, then check whether they are smaller than 1, and then say, no, I don't want to do that. I want a quick way of commenting on the stability of the system. That's the rationale of using Z transform. So we know this is the objective. The objective is looking at the difference equation, find out quickly whether a system is stable or not. Okay? So this is the rationale, and Z transform is used to comment on the stability by looking at the difference equation, a difference equation of an IAR system. Okay? That is the rationale. That is the rationale of using Z transform. So now we'll see how we actually get to the point where by looking at it, we say this is a stable or an unstable system. Okay? Okay. So we know what a Z transform is. For the convenience, the convenience is that we have said that it is basically about this R which runs with an exponential, and then you take the Fourier transform, and then you basically, this is still the Fourier transform, and this R, instead of writing it here, I can always write it right, because it was divided by r raised to the power n, so you bring it up, and I want to put it with an exponential, so I do that. I say, because n here, minus minus, so I put a r exponential j omega minus n, right? And this r exponential j omega minus n is, we call this term inside the bracket as z minus n, and this is what the Z transform is. So another interpretation of Z transform is that you take x of n multiplied with r of minus n, multiply it with an exponential. A signal, take signal, multiplied with an exponential, you define it, and find the ranges of r for which you can make it converge. The signal multiplied by r minus 1, and that is what our interest is. And this is in polar form. If you remember, polar form is r exponential j theta. This is the radius and theta is the frequency. So omega is the discrete frequency which runs from 0 to 2 pi. So we know that. Okay. So Z transform is in fact this. And to plot it, usually a polar coordinate is used. So this is, you put a value of r, you have a theta, so you get a value. So this is a 3-dimensional transform. Fourier transform is a 2-dimensional transform. You put omega, you get the Fourier transform. Here you need to put r, you need to put theta, and then you get a point. So the points, this will be a surface. That's why we don't want to get into that. You will get a surface, 3D surface. What is the point? In looking at the surface is no point. So, but r is important, that where it converges. So we'll see what r needs to be. So this is the Z transform. It is the Fourier transform for r is equal to 1. It helps us to decide about the stability of our system. Yeah, unstable system. Okay. Okay, good. So we know x exponential j omega x, and this it requires that the sequence should be absolutely summable. So we need to extend it such that it can be used as a tool to analyze digital systems in general. And this is what you introduce an r raised to the power minus n, multiply it with the signal, and now you can make r to make this whole thing converge. And this is an example, 2n u of n. You introduce this r of minus n. This you cannot calculate the Fourier transform, and by an appropriate value of r you can make it converge, and that value of r is greater than 2. So r greater than 2, you can actually compute the z transform, and this transform is the z transform, is introducing a factor r. So this is where r is introduced, and this is the formula. X of z is x of n, z of minus n. This is the z transform. Example, let's say I ask you find the z transform of 2 of n u of n. You say okay, the formula for z transform is x of z, z of minus n, n goes from minus infinity to infinity, x of z. This is the formula. So you put this in the formula. You say n goes from minus infinity to infinity, 2 raised to the power n, z of minus n. Because of u of n, you run this summation from 0 to infinity. You rewrite it as n goes from 0 to infinity, 2z minus 1 raised to the power n. And you know this is alpha raised to the power n. An infinite summation is what? 1 over 1 minus 2z inverse, where 2z inverse magnitude is less than 1. 2 over z less than 1, it means 2 is less than, or z must be greater than 2, and z magnitude is greater than 2. Z magnitude is in fact r must be, because z is the complex number r exponential j omega, in that the magnitude is r. So usually we draw it. So this is z transform. The point which I was making here, you write 1 minus 2, z is what? R exponential j omega raised to the power minus 1. You can actually compute z transform. How to compute z transform? Put a value of r, value of omega, find a value. Put a value of r omega, r omega, r omega. Keep changing r, keep changing omega. So you'll find all the values. And you can plot those values. Obviously they'll be 3D, right? Because you have an r, you have a theta, and a value. R theta, a value, a value. So for every value of r and theta you have a value. So it will be a surface, 3D. But we don't do that. We don't plot or compute, so to say, z transform. We don't compute or the different values of z transform. But for the Fourier transform, we actually compute Fourier transform. Put a value of omega, find a value. Put a value of omega, find a value. Okay, so this is the difference. You are just happy with this expression, and you are happy with this, knowing whether it has a unit circle or not. You are just happy in finding a region of convergence, so to say, where it will converge, and that convergence is if it is greater than 2. And you always plot this circle, which is called a unit circle, to see whether this unit circle is inside the region of convergence or not. If it is not, you say it is an unstable system. Unstable hai. But we can just, looking at this, we know it is unstable. Say na? Namaskar. Okay, so this is what how you compute the z transform. So z transform in general is computed to find the region of convergence. Okay, so for A of n, U of n, and this is how you write a Z transform is 1 over 1 minus A Z inverse. Okay, and you say the region of convergence. This is the Z transform, and the unit circle is important, so you say whether it has a unit circle in the region of convergence or not. Here is an interesting example which says find the Z transform of minus A of n U of minus n minus 1. So I'll not do this, but if you do this, run through this example, you get the same Z transform, 1 over 1 minus A Z inverse, right? So the issue is that if you take Z transform of A of n U of n, it is Z transform is 1 over 1 minus A Z inverse, where the Z magnitude must be greater than the A magnitude. This is the region of convergence. Z magnitude must be greater than the A magnitude. If A is 2, outside 2. If A is 3, outside 3. If A is 0.9, outside 0.9. Then if you compute Z transform of minus A of minus n U of minus n minus 1, it turns out to be same. The only difference is in the region of convergence. E magnitude is less than A magnitude. Okay. Now this is a right hand side sequence. This is a right hand side sequence. If you plot it, if it converges, it is this sequence. 1 A square, A cube, and it goes like this. Whereas this is a left hand side sequence. Right? If you plot it, it will be moving in this direction starting from 1, minus 1, minus 2, minus 3, whatever. Because U of minus n minus 1 and minus will make it go in the negative, provided A minus n depending upon this, but this is what it is. Same Z transform. So Z transform is not unique, but it is the Z transform in region of convergence which makes a Z transform unique. This is how you plot the region of convergence. You say plot a circle with radius A, and anything outside the circle is the region of convergence. This is how you plot this. You still plot A. Anything inside this is the region of convergence. So any value of R inside less than A will make the Z transform converge. This also tells us a lot many things, and this is how it will help us to understand the stability. Okay, these are the two expressions. Remember, you need to plot the unit circle. If unit circle is inside the region of convergence, we say system is stable. If not, we say system is not stable. Number one. Number two is, looking at this, you can compute the pole of the system. Pole is the roots of the denominator. What is roots of the denominator? A. If you say 1 minus A Z inverse is equal to 0, so it is 1 is equal to A Z inverse and Z is equal to A. So Z transform is in fact written in this peculiar manner that roots are always this, with the negative sign. This is always the root. By, in fact, instead of doing this, it was written like this. By looking at it, you know this is the root. Okay? If this is the root, let's say A is 0.9. So you can actually go and plot the root, and you say A is 0.9. If A is 0.9, you plot the root of the denominator, and root of the denominator is called the pole of the system. Okay? The root of the denominator is called pole of the system. Root of the denominator is called pole of the system. Let me just recap what I'm saying. I'm saying you have a sequence. You take its Z transform. A Z transform of sequence will always have something in the denominator. Numerator is not important. Numerator is not important from checking stability. The denominator, the roots of the denominator, they are very important. What are the roots of the denominator? Looking at the roots, you can say so many things about the system, whether it is low pass, it is high pass, it is band pass, it is stable, it is unstable, it is close to unstable, it is very stable. So by just looking at the pole location, you can say a lot about the system, right? And that's the pole location is very important. So you need to understand, looking at a pole, you say, okay, it is this. Looking at the pole, you say it is stable, it is unstable, it is this, it is that, low pass, high pass, whatever. Right? So the pole is important. This is how you get to the pole. The pole is that the roots of the denominator are called poles, and roots of the numerator, they are called zeros of the system. Okay? This is important. I wanted to make this out. A pole will never be in the region of convergence. A pole can never be in the region of convergence. Why? Because if you put value of z equal to 0.9, what will it make? Z, because pole means that if z is equal to 0.9, it is 0.9 divided by 0.9, it is 1, 1 minus 1 is 0, 1 over 0 is infinity. So it is infinity. The Z transform will shoot up to infinity if your value of R is R and omega is approaching, this value will just shoot up. And that's why as it makes a pole, it is called pole of a system. So it makes a pole of a system. It is, so a root is important while computing Z transform, and this is what the root is, and this is why we compute Z transform to find the poles of the system. We compute Z transform to find poles of the system. Okay, so we'll keep hitting this, but this is important that Z transform is not unique. A Z transform is not unique. Two different sequences may have same Z transform. One will be a right hand side, the other will be a left hand side sequence. Given this, now let's go in the other direction. Given this, if I ask you only this information, if I ask you find the inverse Z transform, what will be the answer? There are two possibilities. One is this Z transform is for a right hand side sequence or for a left hand side sequence. So you always give two answers. This is important. You always give two answers. You say its inverse Z transform may be an, or in this case 0.9 n u of n, or minus 0.9 minus n u of minus n minus 1. It is this. So two options are there, and you mention both options. And this you say if region of convergence R or Z magnitude is assumed to be greater than 0.9, and this is if Z magnitude is assumed less than 0.9. So you have two options depending upon the region of convergence. If region of convergence is missing, is not given, then you got to give two answers to the question. Otherwise you just give one answer. So this is the Z transform, and this is how you compute it. So let's go ahead with, so this is the Z transform of minus a n, sorry there is no negative sign here, minus a n u of minus n minus 1. Should go through this as same Z transform, and the only difference is because here is this is the magnitude, this magnitude must be less than 1, and it turns out to be Z is less than a, so it is inside the unit cell. The left hand side sequence region of convergence grows inward. Left hand side sequence region of convergence grows inward, and for right hand side sequence it grows outward. Okay, so but this is what we need to remember, and this is another example. Minus 1 over 3 n u of n is a right hand side sequence. Minus 1 over 2 n u of minus n minus 1 is a left hand side sequence. So you have a combination of two sequences. So you compute Z transform of this, Z transform of this, region of convergence, and then you say, so how to compute Z transform? I know this is A of n u of n, so Z transform is 1 over 1 minus A, which is minus 1 over 3, so minus minus is plus 1 over 3 Z inverse. Negative sign will go with this sequence, it should be a positive sign. And 1 over 2 n u of minus n minus 1 over 2 n u of, as again has a Z transform 1 over 1 minus 1 over 2 Z inverse. In this case the root, what is the root in this case? Minus 1 over 3. So minus 1 over 3 is here. And region of convergence is greater than 1 over 3. This is a right hand side sequence. So greater than is everything outside 1 over 3. What is the roots here? It is 1 over 2. So 1 over 2 is here. So region of convergence is inside. Everything inside the unit circle. So a combination. So you take intersection. You say, okay, so means a value of R needs, one value of R needs to satisfy both. One R, because now we have an R here, while computing the transform an R here. I want to find a value of R which makes both converge. Okay, if I make a value of R which is greater than minus 1 over 3 or 1 over 3, so to say, let's say 1, it will definitely converge this. Put R is equal to 1 here, it converges. So R is 1 will converge this, but if you put R is equal to 1 here, it will not converge. 1 over 2, put negative values of n, it will grow. So the intersection which is between 1 over 3 and 1 over 2, take any point here, both will converge. And that is what is important. So if you have multiple poles in the system, these are poles. If one is a right hand side sequence, its region of convergence will move outward. If one is a left hand side sequence, it will go inward. Then the intersection of these two will give you a region of convergence. If let's say all of them are right hand side sequences, what will happen? This is an interesting case. Let's assume.
Yeah, in this case, we don't care about the unit circle.
No, we care. This is not a stable system. Because
If the unit circle lies in the region of convergence of both the signals,
the
then only is the system stable.
precisely, if one lies here, because one will not make this converge, so you cannot compute the Fourier transform of this. So a combination. So you need to look at the intersection of all the region of convergences, and then you say whether it is stable or not. So intersection, and there may not be any intersection. For example, if it is 1 over 6, what is 1 over 6? Something here. So its region of convergence is this, and 1 over 3 region of convergence is this. So there is no value of R which can make both of them converge. So the Z transform does not exist. A Z transform does not exist in this case. So you cannot just write this is my Z transform. No, there is no Z transform because it does not exist. There is no value of R, one value of R that can make both of these sequences converge. One value of R, because it requires values to be less than, and this requires values to be greater than. So there is no intersection. So no region of convergence, no Z transform. Z transform you cannot compute. If so, there is a possibility that you cannot compute the Z transform. But our really interest is in systems where you have multiple of these, multiple of exponentials. For example, if this is 2, then region of convergence contains the unit circle, so it's stable. No. It's the entire region is the region of convergence. Any value of R between 1 by 3 and 2.
So unit circle is stable side from 2.
G, but unit circle must be contained. Okay? It does not matter where it lies. All matters is R is equal to 1 will make both the sequences converge? Answer is yes. So it is a stable system.
1 by 3 से लेकर 1 तक जो उसका फोरियर ट्रांसफॉर्म है वो हम कैलकुलेट कर उसके बाद तो
G. So to say, if you introduce R, the question is that if you introduce R, you can compute the Fourier transform by putting values of R equal to between greater than this and less than this. Yes. Okay? But R, because 1 is not in this range, so you cannot compute the Fourier, the real Fourier transform, and so it's G. Only stability. The question and confusion is that what a unit circle is doing here, nothing. Unit circle is a test. So you make region of convergence, drop the unit circle. Check whether unit of the unit circle is in the shaded region or not. If it is, you say system is stable. If it is not, you say system is not stable. Let me give you an example, and that will help you to understand it better. Okay. For example, there is a sequence, a system, where this is the impulse response: 0.2 n u of n minus 0.6 n u of n plus 0.9 n, or I can put a plus, and here minus 0.9 n. This is 3 exponentials. As I said, this is very real. Okay, but they will not appear like these in the actual difference equation. They will not appear like this. Okay, but this is a very valid impulse response, and infinite impulse response with how many exponentials? 3 exponentials in it. Okay, so compute Z transform. What is the Z transform? Z transform 1 minus, and what is the region of convergence? Okay, then comes this minus 1 over what is the region of convergence? Right? This 1 plus what is the region of convergence? Greater than 0.9, magnitude, because it's a magnitude, so you take greater than 0.9. Okay, so this is the region of convergence. What is something which is should be greater than 0.2, greater than 0.6, greater than 0.9? What is that? It must be greater than 0.9. Okay, so you can draw poles. So you say one pole is at 0.2, one pole is at 0.2, the other pole is at 0. So this is a pole at 0.2, other pole is 0.6, and other pole is minus 0.9. If all these sequences are right hand side sequences, so all these sequences, very easy to compute the region of convergence. How? It is always outside the outermost pole. Region of convergence is always outside the outermost pole, because it must be greater than this and greater than this and greater than this. So what is that? That is something which is greater than 0.9. And then there is a unit circle. Is it inside the region of convergence? Answer is yes. Very easy check for stability. The check is for, and usually we will have right hand side sequences, because left hand side sequence is not causal. It requires future sample. So we know that h of n in negative direction means non-causal, requires future sample out. So we are mostly in practical, not from academic perspective. In academics you can get sequence left, right, but from academic perspective h of n is always right hand side sequences, many exponentials. Region of convergence is outside the outermost pole. So if somehow you compute the poles which are here in the Z transform, still I need to relate this to the difference equation, which I have not done up till now. Okay, we'll do that. But an easy check, if you are given h of n, though by looking at this you know that is there any exponential which is greater than, which has a which is greater than 1. One way is that. The other way is that in Z transform, plot all the poles, plot unit circle, find out if all the poles are inside the unit circle or not. If they are, system is stable. If they are not, the system is not stable. So in MATLAB you can plot, looking at the difference equation, ask MATLAB to plot pole 0. MATLAB will plot all the poles. See whether all the poles are inside the unit circle or not. If they are, you say system is stable. If not, then system is not stable. Okay. So the location of the pole, the outermost pole. So there may be 99 poles which are inside the unit circle. There is one pole which goes out. It will make the system unstable. Okay. So it's very easy to comment on the stability of a system by plotting all the poles and seeing whether all the poles are inside the unit circle or not. This checks the stability for a causal system. For an anti-causal system, all the poles must be outside the unit circle. All the poles must be outside the unit circle for a system to be stable. Because inside, so region of convergence is inside the innermost pole. For a two-sided sequence, the outermost pole of the right hand side sequence and the innermost pole of the left hand side sequence should be the outermost pole of all the right hand side sequence must be inside the unit circle, and the innermost pole of the left hand side sequence must be outside the unit circle. Means all the poles of your right hand side sequence must be inside the unit circle, and all the poles of left hand side sequence must be outside the unit circle for a system to be safe. It's a simple check. If that is there, you can say that this system is a stable system. So I can put as many as I want, plus 2 raised to the power n u of n minus 1, provided the pole is outside the unit. This tells me this is a left hand side sequence, u of n, u of minus n minus. So easy check. So plot all the poles, see all these poles, the right hand side sequence inside the unit circle, all the poles outside the left hand side sequence outside the unit circle, and the intersection will be, what will be the intersection? Outside the outermost and inside the innermost pole will give you the region of convergence, and this region, a ring shape, will contain the unit circle for sure. Otherwise it will not. If it disobeys any one of these, if there is something which is, so if there is something where any one, if it goes out or this comes in, it will not be a stable system. Right? So still again we need to relate this to the difference equation, which we have not done.
So in control systems we had learned that all the poles should be on the left hand side, and now this
जी मैं आपको बताता हूँ. The question is, in control system they have learned all the poles must be in left hand side S plane. That is the Laplace transform. All the poles must be in left hand side S plane, and once we will learn converting h of s to h of z, we will learn that all the left hand side must get into the unit circle for a system to be, for a transformation to be stable. Okay? So you usually design the control system in h of s. All the control systems are designed in h of s. Now you cannot implement h of s using a computer program, so you need to convert it into z domain. And how you do that? There are transformations, but the transformation that guarantees that a stable system in continuous domain will only be stable in discrete domain if all the poles here will somehow get inside the unit circle. So this is the difference between the two. And the unit circle is what? It is the Fourier transform. So if you look at the Z transform, it is a surface, right? I've been telling you Z transform is, in fact, though we are not plotting it because we need not to plot it, but if you plot it, so it will be, let's say this is the region of convergence. Nothing will be inside here. You cannot put an R which is less than this, because that is not a valid R. R should be greater than this. And for every value of r, you put all values of omega, they put all values of omega. So keep doing that, it will form a surface coming outside the board. This is the surface. Now here is the unit circle. And the Z transform of the unit circle is the Fourier transform. So what you do is you put a ring of unit circle and take the surface out, a cross section of this. That is the Fourier transform. Okay? And you lay it down straight, and you see, what you see is what? The Fourier transform. This is the cross section of a Z transform at r is equal to 1. The Fourier transform is Z transform at r is equal to 1, and this is the only Z transform which we are interested to compute. Put r is equal to 1, compute. Then why to put it in 3 dimension? Because this is the, so you just put it straight. So straight line may you draw it like this. Otherwise it is running on the unit circle in 3 dimension. Okay, it's the 3rd dimension basically, but r is equal to 1, you put it straight, and that's what the Fourier transform is. Okay. Okay, so here is the which you started with. So these are some common Z transform. Again, you can put it on your cheat sheet for the exam. Delta of n is 1, u of n is 1 over 1 minus Z inverse. The region of convergence is important. Minus u minus n minus 1 is the same, but the region of convergence is now less than 1. Delta n minus m is Z of minus m. A and u of n is 1 over 1 minus a Z inverse. Magnitude Z is greater than a magnitude, and this same, but its region of convergence is inward. And n a n u of n is this a Z inverse 1 over 1 minus a Z inverse square. So these are some useful pairs for Z transform. And interesting, transform हो गई. Yep. नहीं इसने किया, इसने भी हुआ है. It is cosine of omega naught n u of n is 1 minus 2 cosine omega naught Z inverse plus Z minus 2. This is in the denominator. Okay, so a second, this is important. If you are finding a second degree polynomial in the denominator, it means that there is a cosine with an exponential. Usually this is of interest to us, r of n cosine of omega naught n, because this is interesting. Let me write it down here. R of n cosine of omega naught n u of n. This is a real system. This is, we are talking about system. What is the system? It has an exponential and a cosine. They are being multiplied together. So if you plot it, it is a system where you have an exponential decaying and a cosine inside the exponential. This is an r of n cosine of omega naught n. Okay? So basically a sinusoid which is decayed with this exponential. So it's a decaying sinusoid. This is what it is. Its Z transform will have two poles. It is 1 minus 2 cosine of omega naught Z inverse plus r square Z minus 2 in the denominator, and in the numerator 1 minus cosine of omega naught r Z inverse. Okay, let me, this is important, I show you this is what it is. So it's the Z transform is here. So Rn cosine of omega naught n has this Z transform, and its region of convergence is Z magnitude greater than R magnitude, whatever this R is. This is not the Z transform R, this is the R which is running with the cosine. So this is R, must be this. Means it should be a decaying exponential, it must not be an But the important thing is, now this is the expression, and where here you see R square. If I write like 1 minus 0.9 Z inverse, and this is interesting now. We have even a publication in this. Though it's difficult, but for the second degree polynomial, once I write y of n, this is the coefficient of y of n. This is the coefficient of y of n minus 1. This is the coefficient of y of n minus 2. Similarly, if there is another one, where that will be a coefficient of y of n minus 3 and minus 4, and these are the coefficients of the difference equation. At least for this first degree, it's very simple. You know, by just looking at this, you can tell whether the system is stable or not. But for a second degree polynomial, it is not that simple. But I know here is r square, so 0.8. If I take square root of 0.8 and it is less than 1, I say system is stable. By just looking at this expression in a second degree system, I can comment on the stability of a system. Why? Because I know this is r square, and r z must be greater than r, and for it to be stable, it must be inside the unit circle. जी जी
उसकी रूट टर्म फाइंड कर सकते हैं.
जी बिल्कुल कर सकते हैं. Yes, you can find the roots. I am saying without finding the roots, by looking at this, you can say whether system is stable or not. Okay, second degree polynomial, you can just looking at what comes with z minus 2, you can comment whether system is stable or not. But these are important pairs. I am just telling you their significance. Though from just from the academic perspective, you need to know that inverse Z transform of this is this. Okay, if I give you this, okay, I put something here as well, and I ask you to find its inverse Z transform. It is this, but what is R? You need to figure that out. What is omega naught? You need to figure that out. So R, you can find it from here, and this is R 2 cosine omega naught the inverse. So omega naught you can find from here. I mean, you can find, or you do other things. Other things are that you make factors, you remove factors, then you take Z transform of this, Z transform of this. As we know that you have two Z transforms, and then take inverse Z transform of both and find the Z transform. But these are some pairs, so you may want to look at these pairs. Ji sir. Stability is that Z must be Z magnitude for a system to be stable. Z magnitude must be greater than R, not the Z transform R, but this R, which is the, okay, and this R is appearing here in the R square. I'm saying in the denominator, what you see with Z minus 2 is in fact the radius, a region of convergence, where the region of convergence is outside that radius. Check whether that is less than 1 or not. Okay, if it is less than 1, then the system is stable. So these are the properties of region of convergence. And I'm again re-emphasizing that the region of convergence is important, because you compute Z transform only to know region of convergence. Okay, because region of convergence and stability. So in general, region of convergence is a ring. We have seen this, it is a ring. It may be inward, outward, or an actual ring for especially two-sided sequences. Its exponential, x exponential j omega means Fourier transform exists only if region of convergence contain unit circle. If region of convergence contain unit circle, then you can compute the Fourier transform, means system is stable. Okay? Region of convergence cannot contain a pole. It cannot contain a pole. A pole cannot be placed in the region of convergence, because region of convergence by definition is the region where it converges. A pole by definition is a place where it does not converge. So a pole cannot be in the region of convergence. For FIR sequence, entire Z plane usually is expected except 0 or infinite in the region of convergence. So no fun in finding Z transform for finite impulse response sequence. It does not convey anything. Okay, I'll find one. I'll tell you by looking at the sequence. You can say that this is a Z transform. So Z transform, you don't do it for FIR systems. Right-sided sequence, the region of convergence is outside the outermost pole. For left-hand side sequence, region of convergence is inward, inside the innermost pole. For two-sided sequence, it will be a ring between two adjacent ring, one for the right-hand side and the other one for the left-hand side sequence, and is a connected region. You cannot say this is the region of convergence, this ring and this ring. No, it is not possible. It got to be a connected region. Region of convergence cannot be disconnected. ठीक है कि आप कहें इसमें तो नहीं है लेकिन इसमें यूनिट सर्कल है, so region, this is not possible. Okay, so these are some important properties. Now let's say we know, if I only give you location of poles, I don't tell you that whether the sequence is, every pole means an exponential. Remember, now you need to correlate, because this is what you will see. All the time you see poles. Every pole represents an exponential. If you are not given a region of convergence, for example, we started here, A of n, U of n, and you said Z transform is 1 over 1 minus A Z inverse. You say region of convergence is A, and you plot the pole. Let's say pole is here. You say outside the outermost pole. Okay, so every pole represents an exponential. For a right hand side sequence, it is outside the outermost, outside the pole. Region of convergence outside the pole. But looking at this now, you can say this. It is in fact, this pole represents this Z transform, and this Z transform represent the sequence. Similarly, this may represent this, minus A of n, U of minus n minus 1 results in the same Z transform, but region of convergence is this. So if only given a pole, you have two answers. If only given a pole, you have two answers. One is you say, okay, pole is given, but the region of convergence, if outside the pole, then this is the answer. If I assume region of convergence inside the pole, then this is the answer. This is good. So for one pole you have how many answers? Two answers. What if you have two poles? So how many possible answers are there? One is both are left hand side sequences, one answer. The other is both are right hand side sequences, second answer. Third answer is this is third answer. Can this be an answer? This is inward, this is outward. No, because region of convergence will be empty. Though this may be, but here it is not. Because there will be no region of convergence then. If you make that one left hand side and the other one right hand side, there is no answer. So you make this right hand side, this left hand side, yes, there is an answer. So given just poles, and I ask you to write all the possible answers, you should be able to do that. Okay, you say answer 1, assuming this, answer 2, answer 3. If there are three poles, how many possible answers do you have? Not really. Not really. So you say inside the innermost, all left hand side, one answer, fine. All right hand side, outside the outermost pole, second answer. Third answer is these two are left hand side and this one is a right hand side, so you will get something in between. The other one is these two and that's it, right? Otherwise if you say this going that way is not an answer, both going that way, this going this way, not an answer. So these are the possible answers which you say, and you can write them down. You say, okay, these are the possible answers. For this you have this answer, here this answer. So means by now looking at the poles, you can at least create all the possible answers for the impulse response. Looking at the pole location, number one. Number two, looking at the pole location, you can comment upon the stability of the system, the region of convergence. Okay, looking at the poles, very simple rule for causal system, all the poles must be inside the unit circle. Very simple, all the poles must be inside the unit circle. It's a very, very simple rule that, so these are the four possible answers and there are only four. One is all are right hand side sequences outside the outermost pole, all are left hand side sequences inside the innermost pole. So these two are left hand side sequences, right hand side sequences, and these two are right hand side sequences and left hand side sequences. So these are the four possible answer. For every answer you can in fact write an actual answer, and that is, for this the answer is A of n, U of n plus B of n, U of n plus C of n, U of n. So you can actually write the answer, that this is the answer. Similarly for this you can write the answer, right? It is minus A of n minus B of n so these are the possible answers, right? So for similarly you can write an answer for this and an answer for this. So these are some of the properties of Z transform. Linearity is one. We already know this. Linearity simply says that if you have two sequences, their Z transforms obeys linearity. Okay, you say Z transform of this and Z transform of this is Z transform. So if you combine them together, you also combine the Z transform, because the mathematical expression used to compute Z transform obeys the linearity, and the region of convergence obviously will be the intersection of the two region of convergences. A delay will not change the region of convergence, because it's got to be absolutely summable. A delay is not changing the absolute summability of the sequence. It only adds as there in the Fourier transform a z minus n naught, a phase term, so to say. So a delay in time is the same z transform, but now multiplied by z of minus n naught. For example, if I ask you what is the z transform of n minus 5 u n minus 5. Okay, this is a sequence which is being delayed 0.9 n u of n being delayed by 5 time units. What is the z transform? And you say, okay, I know the z transform of 0.9 n u of n, which is 1 over 1 minus 0.9 z inverse, and always write the region of convergence. A delay in time is multiplication by a z of minus 5. So this is the answer. Okay, a z of minus 5. So this is a property, and now it is shown, the example is given in the other way, that if you are asked to compute inverse z transform, you see a z inverse here, you don't like it because you know the inverse z transform of this expression, so don't worry about it, hide it, throw it away. Compute inverse z transform of this, which is 1 over 4 n u of n, and a delay, and z minus 1 means every n is replaced by n minus 1. So you say now bring it back, and this is the answer, 1 over 4 n minus 1 u of n minus 1. Okay, and region of convergence is not going to change. So this is an important property. So then there is a property, what if you multiply a sequence with an exponential, okay, a complex exponential, z naught is this is same as we have seen in Fourier transform, where we saw that if you multiply a sequence with a complex exponential, it is shift in frequency, remember? So shift in frequency is multiplied by exponential. So this is same here. If you're multiplying with a complex exponential, you are dividing every z in the z transform by that z naught. It translates to the same property, because exponential, once you go up, you subtract so it's the same question. For example, I give you this, the z transform of u of n is 1 over 1 minus z inverse, where region of convergence z is greater than 1. What if I multiply it with an exponential? So I say 0.9 n u of n, and this tells me that every z you see should be replaced by z over 0.9. Okay, every z you see, you replace it by z over 0.9. If you're multiplying it with an exponential, you say 1 minus z over 0.9 inverse z over 0.9 greater than 1. So z inverse 0.9 minus inverse, so minus comes out, 1 minus 0.9 z inverse, z magnitude is greater than the same, we know. Okay, so it's another way of going and doing this, that multiplication by an exponential is the same z transform, but z is replaced by z over r or a in that expression. So it's changing this. So this is another important property which tells us about what happens if you multiply a signal with a complex exponential. Obviously you are changing the roots of the system. This is important. Multiply with an exponential, you are changing the roots. A system may be unstable, but you multiply with an exponential, it will bring the root inside, because z divided by now z naught. That's what I did, right? U of n is an unstable system. It's unstable system, but I put 0.9 n, it becomes a stable system. So multiplication, why? Because you are changing the roots, you're bringing the roots in or out. Okay, so it's multiplication by an exponential can make a system stable. Here another example is given, which is cosine of omega naught n r of n. Know the cosine of omega naught n z transform and replace every z by z over r. You can look at this example. Then a simple property which we have seen in Fourier transform as well, n x of n. If you have a sequence and multiply it with the RAM, 0, 1, 2, 3, 4, 5, 6, 7. Okay, if you do that, so all you have to do is the same Z transform, but you take its derivative and divided by minus 0. So region of convergence is same as the region of convergence. And this is an example which is done to, which uses this property. This perhaps may have some academic value, but usually I'm not really too concerned about this. So G. G? It will not, because if it is a decaying exponential, you multiply it with the RAM, it will bring it down. ठीक है ना? Because something which is going down, you multiply it with the RAM will not affect the RAM. Okay, then the conjugate of complex sequence is just for completeness that you take the conjugate. So you take the conjugate and the conjugate of replace every Z by Z conjugate, and whatever you get, again take the conjugate. That again we have seen this in the Fourier, and it's more important in the Fourier transform. Same is the case with reversal and conjugate. You take reversal conjugate, you replace every Z by 1 over Z, then replace Z by Z conjugate, then take the conjugate of everything. So that will give you the answer. And this is, if only flip, is replace every Z by 1 over Z. For example, if I ask you what is the Z transform of 0.9 n u of n, you say it is 1 over 1 minus 0.9 Z inverse, where Z magnitude is greater than A magnitude. Then I ask you, what is the transform of this? Now what is this? This is a left-hand side sequence. Simple, you replace every Z by Z inverse. Okay, so it will automatically 1 over Z, it will go there, it will come here, the sign will change, and this is the expression. So we are not used to seeing this. We are used to seeing A of minus, A of n, U of n, minus n, minus 1. So that is crafted to give you the same Z transform. But here I'm saying if you flip in time, you replace Z over 1 over Z by 1 over Z. The region of convergence will automatically change to inside. Z is less than 1 over A. Okay, but the poles are at 1 over A now, because it is 0.9 Z. Find the pole. It is at 1 over 0.9. This is important. Convolution property says, though you don't use it obviously because you are not computing Z transform, but the convolution property says multiplication in time is convolution in Z domain, or multiplication in Z domain. Convolution in time is multiplication in Z domain. This is the convolution property. So I think this is where so we have few things left, but just to give you a quick, this is what really we wanted to do. We wanted to go to a place where we talk about the difference equations, which will come when here. Okay, once we talk about the difference equations and bring the difference equation in this form. Difference equation, take the Z transform of the difference equation, bring in terms of h of Z, and h of Z will be something very, very familiar to you. 1 over 1 minus A Z inverse. So that once you take inverse Z transform, you get the. So from the difference equation, we'll get to this expression. From this expression, we'll get to seeing all the poles of the system. Film khatam hogi?